section 10.3, and it's called Logarithmic Functions. So just some basics to get started. Definition of a logarithm is just a logarithm is the inverse of an exponential. So just to help you understand, at this point, we already know a few inverses. We know that addition and subtraction are inverses. If I gave you a problem and it was x plus 2 is equal to 5, you would subtract 2 on both sides and tell me x is 3. That's how you would get the answer. Multiplication and division are also inverses. If I told you 2 times x is equal to 6, you would divide both sides by 2 and say x is equal to 3. That's the answer. When you square something and the square root, those are also inverses. If I told you the square root of x is equal to 2, you would square both sides and tell me x is equal to 4. So by the same token, this is why logs exist, because if we have a problem where it's 2 to the x is equal to 5, what we do is we use logs to solve. We'll be going over how to do a problem like this in a minute. If you do have your calculators, why don't you get them ready to go, because we will be needing calculators later in today's lesson. So the first property I wanted to show you with logs, by the way, logarithm is just a longer way to just say log. So log is, if I say log, we know that means logarithm. One property to get started is something called the translation property. Translation property just says that if you have a base to a power is equal to an exponent, this is the same thing as saying log base a of y is equal to x. This is called the exponential form. And this is called the logarithmic form. It's important to note that these numbers are called bases. These numbers are called the exponents. And the y is just really called an argument. The argument must be greater than 0. So you can't take the log of a negative number. That's what that means. Let's go through some examples. Those two examples, we're going to just say convert exponential to logarithmic form and vice versa. So for example, if I gave you a problem in exponential form, write it using logs. And if I gave you a problem using logs, write it using exponents. One way that's really quick to do this is I just call it the crisscross. If you just put your pen or pencil on the base a and do a to the x power is equal to y, that's how we convert it every time. Easy enough. So do a couple of these. What about if I told you log base 3 of 81 is equal to 4? We just want to write this using exponents. How could we do that? Yep, 3 to the 4th is 81. I had just said if we use our crisscross technique, 3 to the 4th power equals 81. And if I were to give you a problem in exponential form, let's say 2 to the 3rd is equal to 8, and I would like you to write it using logs. Think about where the numbers have to go in order for this to make sense. It's always this number to this power equals this number. So the base is 2, so that's going to be the base of the logarithm. 3 is the power, so 2 to the 3rd is equal to 8. That's how you do this. Just so you know the way that we read this, we say log base 2 of 8 is 3. Don't say log 2, 8. You have to say log base 2 of 8 is 3. That's just the proper way to read this. All right, so I have 4 problems coming up, and we're just going to be solving them using our properties of exponents and using the translation property of logs. So the directions are just going to be to solve. We're going to convert radicals or decimals, rational exponents. So we have log base 3 of x is equal to negative 3. What we do to get rid of log is we use the crisscross property I told you about. So we'll just say 3 to the negative 3rd is equal to x. And then you have to try to remember some of the properties that we talked about before. So what happens when you have a negative power? Anyone remember? Yeah, we switch the position. This just turns into 1 over 3 to the 3rd. 3 to the 3rd is 27. And that's how you do a problem like that. What if you had base x of 5 is equal to 4? So again, the way we get rid of log is we do the crisscross. So this would be x to the 4th power is equal to 5. You don't want to know what x to the 4th is, so we could just take the 4th root of both sides. Just get x is equal to the 4th root of 5. Couple more. What if we had log base 36 of the 4th root of 6 is equal to x. Similarly to what we did before, we do 36 to the x power is equal to the 4th root of 6. We left our last class talking about how to do these kind of problems. We want to try to write them using the same base. 36 and 6, we could write 36 as 6 to the 2nd power. And the 4th root of 6, you have to try to remember a property we talked about before. The property was anytime you have a fractional exponent, this just means radical. So if you have the 4th root, logs don't work really well with radicals, so we just convert them to a fractional exponent. So the 4th root of 6 to the 1st is just the same thing as 6 to the 1/4 power. Power to a power we multiply, so we have 6 to the 2x is equal to 6 to the 1/4. In our last class, we canceled out the bases if they were the same. So 2x is equal to 1/4 dividing by 2. Thus, x is equal to 1/8. We want to do one more of these type of problems. What if we had log base 1/3 of 2x plus 5 is equal to 2? Similarly to what we did before, we do 1/3 to the 2nd power is equal to 2x plus 5. One-third squared is just 1/9. This is a basic equation. We could just multiply everything by 9 to get rid of the fractions. And this would just be 1 is equal to 18x plus 9 times 5 is just 45. So just to finish this up here, we can subtract 45 on both sides. 18x is equal to negative 44. Be negative 44 over 18. Or reducing that to be negative 22 over 9. Using the translation property. One other property I'd like to add. So we talked about the translation property over here. One other property to talk about is called the inverse property. So the inverse property of logs just says if you have the same base of a log and the same base of an exponential, those bases cancel, and you just get whatever's left over. Similarly, if you had b to the log base b of x power, these would cancel and you would just get x. We're going to use the translation and the inverse property to do new problems here. So the directions are just going to be to evaluate. So first one is just log base 12 of 144. A couple different ways we could do this problem. 144 is just the same thing as 12 to the second, right? So we could just write this log base 12 of 12 to the second. Cancel these out using the inverse property, because those bases are the same, and then just say the answer is 2. We have log base square root of 3 of the square root of 3. What would this answer be? What is it? It would be 1. Yeah, one thing you could do is you could use the inverse property and just cancel these. But whatever's left over is the power. Right? Another thing we could do is we can make this equal to x and say the square root of 3 to the x power is equal to the square root of 3 to the first. We'll just cancel these. Either way, you wind up just getting 1. 1 would be the answer. We could either use the inverse property from the start, or we could use the translation property and the inverse property of exponentials. Speaking of that, what about if we had log base 3 of 1? Some of these are a little tricky. If you're not sure how to do it, just make it equal to x. Then what we could do is do 3 to the x power is equal to 1. Does anyone know how to finish this? 3 to what power is 1? Or anything to the what power is 1? 0, right? So that's anytime you have log of 1, the answer is just 0. This is the same thing as just 3 to the x is equal to 3 to the 0. X would just be 0. Remember, anything to the 0 power is 1. What about if we had log of 0.4 of 1? What would that be? Right? Because again, we can make it equal to x and do 0.4 to the x power is 1. Anything to the 0 power is 1. So I think we're good with that. What about if we had a problem log base 4 of 4 to the 7? What would that be? Seven. Using the inverse property, we cancel these. The answer is just 7. If we had 5 log base 5 of 6 as the power, what would that be? 6. And a couple more. What if we had log base 4 of 64? I know 64 is a power of 4. 64 is 4 to the what? 4 to the second is 16. 4 to the third is 64. So we can write this log base 4 of 4 to the third, which is just 3. So with log, sometimes you have to change the way it looks in order to use a property. Then one more of these. Log base 3 of 1/9. And we're kind of close. One thing we could do is we can make this equal to x and do 3 to the x is equal to 1/9. This is a similar problem to what we did during our last class, where we try to get the same base. So I know that 9 is the same thing as 3 to the second. And like we said in class, if you want to switch the exponents, the power becomes negative. It would just be 3 to the x is equal to 3 to the negative second, or x is equal to negative second. To finish up, I want to show you how to graph these, and I also want to show you how to do some word problems that you can see on the final exam. So let's talk about graphing logarithms. We talked a little bit about graphing exponential functions in our last class. So remember, y is equal to 2 to the x from the last time we worked together. This graph looks like this. We said that it looks like a hockey stick. The y-intercept was 1. We also had a horizontal asymptote of y equals 0. So graphing logarithms are similar. If we had to graph y is equal to log base 2 of x, this graph's going to look like this. And this graph also looks like a hockey stick. The x-intercept is equal to 1. And then we don't have a horizontal asymptote, we have a vertical asymptote. The vertical asymptote would just be x is equal to 0. What I want to do is just give you a couple different examples of this. What if I asked you to graph say y is equal to log base 3 of x minus 2? Now the minus 2 is on the inside. So if you have a number on the inside, that just moves the graph left or right. If it's negative, remember that goes to the right. And if it's positive, it goes to the left. So this is going to be the same graph as logs that we did before, except this is going to go to the right too. So take a look at our regular log graph. If we're shifting it to the right too, the vertical asymptote from the parent graph, instead of being at 0 up and down, it's going to be 2 units to the right. So that's going to be the vertical asymptote is going to be x is equal to 2. Also, if you look at the parent graph, we said the x-intercept was 1. So if you move 1 2 units to the right, the x-intercept is now going to be 3. And the graph will look something like this. This much as you need to know about log graphs. Let's do another one where we move the other way, and we'll finish with applications. What if we had f of x is equal to log base 4 of x plus 3? Plus 3 is moving to the left 3. So if the graph normally has a vertical asymptote of 0, the graph to the left 3, the new vertical asymptote is going to be negative. If the normal graph has an x-intercept of 1, and you subtract 3 from that, our new x-intercept is going to be negative 2. And then the graph will just look like this. We're not really going to be moving the graph up or down. We're not going to be reflecting it. This is pretty much what you need to know about graphing logs. All right. And I just wanted to finish off with applications. So applications of logs. An example looks like this. Let's say a population of ants grows according to if t equal to 80 log base 10 of t plus 10, where t is equal to days. Initial population of ants. So initial population means that you're just starting. So whenever you see initial population, this just means your independent variable, or days, is equal to 0. And what you have to do on your calculator is we're going to plug in 80 times the log base 10 of 0 plus 10. I don't even know if we need a calculator for this particular example, because what happens when we have log base 10 of 10? They cancel, right? And you just keep the power, which in this case is 1. So 80 times 1 will just be 80. So for this equation to be true, you have 80 ants. Now to finish this, if I asked you for the number of ants present after 90 days. to use our equation, P of 80, or P of 90. And if we plug that in, we're going to do 80 times the log base 10 of 90 plus 10. And we still don't need a calculator. 90 plus 10, of course, is 100. How can we do that without a calculator? Log base 10 of 100. We want to try to make the bases the same, right? So 100 is the same thing as 10 squared, right? So this would just be 80 times the log base 10 of 10 to the second power. Or 80 times 2, which is 160 ants.